My name is Steven Sobieszczyk. I go by Steve Sobi. I am technically a hydrologist, but I've made a recent career out of doing a lot of communication work. And as my office outreach and communication lead, I spend a lot of time in schools. I spend a lot of time at career fairs, at a lot of STEM nights, anything that involves trying to bring science up to people who normally don't see it, don't normally appreciate it. I take it upon myself to try to go out there and engage them as much as possible. So I appreciate the opportunity to come here and talk with you guys. So my presentation is going to be about water awareness, or as the title says, water everywhere. Not really. So I'm going to talk about the world's most abundant yet limited resource. So, first off, water is cyclical, right? So we're going to do some introductions. I'm not sure how much you guys are into studying water or taught water in your schools. So first off, the basics. I don't want to belabor the point too much, but it's pretty simple. So where does water come from? How many people have seen the hydrologic cycle, the water cycle? Excellent. Who wants to explain to me the hydrologic cycle? You in the back, who is kind enough to comment, can you please tell me the three different components of the hydrologic cycle?
You know that song, solid, liquid, gas.
So, the three phases. That's basically it, though. So, throw some terms out for me.
Ice.
Evaporation.
Evaporation, I hear that.
Transpiration.
Transpiration.
Precipitation.
Precipitation. Oh, you guys are so good. Usually the second graders I talk to don't know this yet. So yes, when you're dealing with the hydrologic cycle, it's basically the idea that water exists and moves through different phases and supplies water to the planet. So you have the ocean heated by the sun, evaporates, goes into clouds go into rainfall, it lands back on the surface, flows either across the surface or to the ground, back out to the ocean. Those cyclical. Nothing too exciting there. Glad you guys know this. So now it's time to go into the more interactive and challenging part. So we are on a big blue marble in space, right? Earth is best known for being covered in water. If I were to ask you, and I'm looking for, just throw some numbers out, how many gallons of water are there on Earth? 300 billion trillion, that sounds pretty good. So whoever has the 300 billion trillion person might be aware of something, but if you were to say 300 gazillion, which I'm going to go off my cue, most people don't have that much information, it would still be trillions and gazillions off. So on Earth, roughly speaking, in gallons, we have 333 gazillion, 18 zeros after that. That's how many gallons. So the perspective is going to make it so much more clear. There are 333 million trillion gallons, roughly, which equates to 333 million cubic miles.
How many gallons are stuck in humans?
I don't know the answer to that. A percentage of that, less than 0.004% of that. So, depending on how well you can visualize the volume of water, gallons, of course, is a minuscule component to try visualizing this with. So, cubic miles, mile by mile. There's still over 330 million cubic miles of those. Which, is that a lot?
Yes. Yes.
Ha ha ha. So, things aren't as I always think. How many people have seen the Apple pictures? I love these. I have two daughters, 7 and 9. I always find one of these random ones that throw them out and see. Oh, look at the old lady. Oh no, it's the old lady. So, when it comes to the amount of water on Earth, things are not as they appear. I mean, yes, look at Earth as a planet, and it seems to be covered with a lot of water. 333 billion gallons of water seems like a lot, but really it isn't. Water is, in fact, limited. What are you telling by this? Now, if you take all the water on the planet, from the planet, inside groundwater, from all the animals and plants and things that have water in it out of the sky, and then roll it up into a ball, a sphere, and place it on top of Earth, you would have a sphere that is 860 mile diameter. Some people Kansas and Salt Lake City. Or if you prefer to have things a little bit flatter rather than symmetrical or circular, you can take that amount of water, pancake it down from coast to coast, border to border, and you have a 90-mile deep pancake of water. That is all of the water on this entire planet to cover North America 90 miles deep, and that's it. My favorite analogy that I learned when I was younger, when I was first learning about water, was using the typical chicken egg. You take one drop of an eyedropper, drop that amount of water onto a chicken egg, average size chicken egg, and if it were to coat the entire surface, that is the ratio, that is the amount of actual water on our planet compared to the rocky mass that is Earth. That's the percentage. So it's a very, very thin film that actually covers the entire planet itself. So it may appear, by looking at it from space, that we have lots of water, but it's just a thin veneer that actually covers the surface itself. Okay, these are some numbers you guys are probably all familiar with, I would venture to guess. So roughly speaking, and this kind of varies depending on where you're getting your information from, but about 17% of the Earth is covered by water. Once again, this is just covering, not making up or comprising the planet itself. Most of that, nearly 98% and increasing, is in the oceans themselves. So it is the saltwater, briny, saline. It is water that we generally cannot use, but it does cover and makes the planet itself look pretty. Less than 2% of the remaining water goes into the polar caps and glaciers, so frozen water. The next percentage, less than a half of a percent of the remaining water is stored in Earth's ground surface around the planet as groundwater. And then you're going to have less than that, fraction of a percent that's lakes and rivers, and those, you could ask about how much is in animals and us, 0.004%, less than that since it's more than just humans. That percentage of that 333 billion gallons of water is basically life, people, animals. Okay, so you looked at it like that. Now let's look at pie charts. It's data, right? We're talking science here, so I've got to at least show some real information for you. So if you look at the amount of consumable or usable water, and that's frankly all we really care about. You could say we care about water as a whole, but generally speaking, humans as a species, we care about the water that we can use. What can we use to grow things? What can we use to eat, drink, so forth, power, instruments. Of all the water on Earth, nearly 99% of it is unusable. We cannot access or use salt water, generally speaking, to drink. We cannot use it to irrigate our crops. We're not using it in anything else besides for navigation. Of the water that's actually usable, most of it doesn't come from the ground. That catches some people off guard. I grew up in the Midwest in Chicago. We have Great Lakes. It seemed like there was lots of water. I moved out west, now in Oregon, the Willamette Valley. It seems like we have lots of surface water in all those cases. But generally speaking, around the world, most people tend to pull their water, will pull water from the ground for their supply. So you can kind of look through the other graphs, get an idea of like, oh yeah, that small blue wedge is bigger, and that little blue wedge on the top is that much. So there's just a very small amount of consumable, usable, limited amount of fresh water that we can actually use. And that's important because when it comes to resources, we need water that we can actually use. Okay, kind of alluded to this a second ago. What about all those big lakes? More numbers for you. So if you take the 6th largest, or not even the 6th largest, but the largest lake call in the Siberia, and then the 5 Great Lakes, the quintessential American surface water, freshwater bodies, the 5 Great Lakes. You take those 6 together, they make up less than 50% of all fresh surface water on Earth. So I think it's 40%, we're on about 50%, so about half, a little less than half, of all fresh water. So if you think of the giant rivers with the Nile, the Mississippi, and the Amazon, it doesn't matter. You go into Crater Lake, you bring in some other lakes from Europe and so forth, that's still half of all fresh water, surface water, is made up in 6 lakes across the entire country, or across the entire world. So, water is appealing. So now we're going to go on a slight tangent here. Why are we talking about water? Okay, I'll throw this question out to you. Why do we care about water? Anybody? It's important for life. Very true. What else?
It's fun.
It is fun. So, here's a thought exercise. When you go camping or hiking, what do you do? Where do you go? Next to water. You walk through the woods to get to the water that you're going to. You walk through the woods to see the waterfall that you want to see. You go to the area where you can go paddling, or you can go swimming when it's hot out. The forest is there just to cover and protect the water that we really want to see. So there's an appealingness to it, an aesthetic to water that is very valuable to us as people. A lot of times we do not consider this. We could take it for granted, for example. But we're all smart, passionate, environmentally friendly, and thoughtful individuals here. So yeah, we care about water because it is in fact appealing to us. So what do you think of when you think about water? The beach, okay.
Rivers.
I see fishing, so kind of recreation.
Wakeboarding.
Wakeboarding.
Rain.
Rain. These are all Northwest things with the rain for sure. Taking a bath. Okay. All valid, good answers. So depending on what you're thinking about, you know, once again, the environmental Northwest, we like to be outdoors. So waterscapes. The Columbia Gorge is important, and it's formed with water. That's interesting to us. Crater Lake, interesting to us. We like to go to alpine lakes. We like to go swim in the Washougal or Sandy River when it gets hot. We like to go to areas where water, because we find it pretty, we find it reinvigorating. It's a place that's something that we all can find solace in. We want to go see a nice river, stream, lake, and so forth. So waterscapes are a very important element of what makes water appealing. Water activities, recreation. We go to the coast. You know, how many people have taken their dogs and family and gone to the seaside or Tillamook or something like that? We care about that. We go fishing, we go clamming, we do things recreation, we stand up paddleboarding. That's the thing that's kind of jumped in the forefront of activities in the last 4 or 5 years from what I can see. Sailing, kayaking, so water activities, very important, recreation. I've always had a weird fascination and a fear of bridges. I don't know, I think it goes back to the Lone Parade earthquake with the Bay Bridge collapse. Ever since then, I've been, but Portland is a bridge town. It's known for its bridges, which a lot of people, whether engineering or photograph or photography or just culturally, find that interesting. So there's a sense of urban hydrology that makes Portland and other harbor and port cities very interesting, because we can come out and see things, take pictures. How many pictures of bridges have we seen across the different venues for social media, Instagram, to, you know, coffee table books, and so forth. So there's actually an urban element that we care about. So depending on what your concern or your interest or your passion, we all have this innate sense or interest in water. So we use it for travel and navigation, so it's got a utilitarian purpose. We use it for recreation, for fun, for activities, engagement. We use it for leisure, like laying next to the pool or laying out next to on the beach. These are things that draw us as a chance to unwind and connect with ourselves and with nature. And we find intrinsic beauty. I mean, coffee table books and images. We look at pretty things and we find water and water environments, waterscapes, very, very pretty. But in addition to that, water is also valuable. How valuable, pray tell? What do you think? If you were to put a financial number on, let's just say, water, do you have an idea of what that might be?
Priceless.
Priceless, that is a good one. Let's see if there's any ecosystem services people here. But yes?
Depends on supply.
Depends on supply, location, yep. Uses. So, just a little exercise for you. How much would you pay for water? Gotta keep my, protection copyright here. I don't want to infringe on anything. You guys file lawsuits. So if you take, for example, a simple bottle of water, and if you pay $1.29 for it for the 8 ounces, or sorry, for the 20 ounces, you factor that up to how much it costs for a gallon. You're willing to pay $8 a gallon without thinking about it. Yes, I'm going for a more broad approach. I understand there's a little more passion here about plastics in the Northwest, or in Portland in particular, but generally speaking, people are willing to buy bottles of water, whether at concerts or other venues, to drink and refresh. So you're willing to pay $8 without question. In a lot of cases, it's more expensive than this. You're still willing to pay because we need water in order to live, and it's something that we enjoy. So we had those old cliches back in the day. This is probably about a 20-year-old image of the gas station. You know, $2 is a lot of gas on a leg. You're paying $8 plus for water without even hesitating. So, water is also very, very unique, which is kind of a fun aspect of it as well. So, since you're all teachers, is this correct? Or administrators, or you interact with people, you have friends, family. Useless water information you can share and make your friends think that you're wonderfully smart. First, there would be no life on this planet if it were not for water. Take that. Ugh. So why do we become hydrologists? Because it's the most important job in the entire world. Because without water, we wouldn't exist. And I study water, so I am better than all of you. It's a universal solvent. And if you've heard that term, basically more substances on Earth can be dissolved with water than anything else. Just use Grand Canyon as an example. There's a lot of properties of water that I can talk to offline when I'm not up here. That, you know, why do we soak dishes and sinks in water? Why do we wash with water? Because water has a unique property that everything's really attracted to it, or it's more attracted to everything else than it is to itself. So that makes it very corrosive, because any molecule that comes in contact with water, the water wants to gobble up and take with it. So that's how it pulls stains out. That's how it erodes and cleans off pots that are soaking in your sink. It is the most common substance found on Earth's surface, which makes sense since 70%, 72% of the Earth is covered with it. It is also the only substance on Earth, relatively speaking, that naturally occurs in all three phases. There are a few other ones that can, but that usually takes a little bit of modification. It's not normal, like room temperature type of situation. So water can be in all three phases: ice, water, or vapor. Believe it or not, you don't see this much of this. I don't see it in news coverage, but water vapor is the primary climate variable. It is the climate ameliorator. It is the greenhouse gas most responsible for the conditions on Earth, its temperature, and everything else. So you can hear about CO2 and sulfur dioxide and other, more popular, dangerous elements or gases that people kind of harp on as greenhouse gas, but it's water is the thing that controls the environment for us. Okay, so I'll hand it over.
Yeah, you never see that in any of the reports on climate change or anything. I mean, you're talking about molecules carrying most heat up there for long.
Whether it's reflecting long wave, short wave radiation, like it is without it, there would be no life. This planet itself uses it to sustain its environment for us. So, yes, water is more important than all the other ones that get better news coverage. Water, this is always what I thought was fun. All the water that's on this planet today, minus a small fraction, was here since the planet itself was formed. I thought that was kind of fun. You know, all the comets and all the icy molecules that were forming during the coalescence of the planet itself, all that stuff, all the vapors and gases coming out of eruptions, all the cycle, the different phases. We're not adding new water to the surface. It's not being created artificially. No, it's basically comes from a certain phase and makes its way through. So that glass of water, it may be only a few hundred years old from the lake or the reservoir that you drank it from, but the molecules that made up that water have been here for 4.6 billion years. There is no pure water on Earth. So, what is water? Its molecular structure? H2O. Can you go out to a river, lake, stream, rain molecule, or raindrop, and actually find just H2 and O? No, it does not. It can be formed in the lab, but there's always something else that has to do with that universal solvent thing. There's always some form of interaction that water molecule will have with other elements, whether from the air, you get, acid rain and other molecules that attach to it, all in vapor form, running through runoff, infiltration, percolation. It's always picking up stuff in the ground, and there's always something else in the river, lakes, streams that can connect you. So you're never going to find there's always some form of constituent that adds to water to keep from being pure. And then it's got a kind of rare, once again, not the only thing, but it's the most popular and most common substance that can actually is unusual because when it becomes solid, it becomes lighter. It becomes buoyant, it becomes less dense. Most things will actually get harder and sink when they change phase into something from liquid to gas to solid, not water. Water becomes more buoyant. So So that's also allowed life to form. Another trivia question, why is this property the most responsible thing for life on Earth? As you know, this bit of information. Where was life first found? Or where did it first form? Theoretically. In water, but where in the water?
Oceans.
The bottom. So why do fish, why do animals survive in winter when ice skaters are going across the top of the surface? Because cold water rises, allowing the other water down to stay liquid. So because of the fact that water will remain liquid at depth, it allows things to live below instead of freeze to death and not exist. So that singular property of water becoming less dense as it freezes is probably the most responsible aspect of water to allow life on Earth to actually form and continue. So, water is vital. We kind of brushed across this a few times and got into a little bit more detail, but what does water do for us? We know it's pretty. We know it adjusts and controls the climate, but what else? What do we use water for?
Grow food.
Grow food.
Hydrates.
Hydrates.
Carry a lot of molecules.
Carry a lot of molecules.
Energy.
Energy. We got dams. What are those for?
Yeah, but it's also part of photosynthesis.
Yeah. So, water provides a lot of different resources that are important to us as people. First, agriculture growth. There would be no food, at least good, relevant food, on Earth without water. So whether it's plants or animals that feed on plants that we then consume, all that material on Earth would not exist had it not been for water. All life forms, whether plant or animal, rely on water to maintain and exist. We have other, infrastructural uses. We get most of our energy in the United States through dams, power generation, through hydroelectric, especially here in the Northwest. So, power production, municipal water supplies, drink. We need to consume water in order to survive. We all know, you can survive like 3 weeks without food and 3 days without water or something. There's some basic rule about that, and we need this in order to survive. We can make do with a lot of the other stuff without having to apply the other stuff. And then there's also aesthetics. I mean, how many times have you seen water features, whether going out to waterscapes, but also fountains? Why do we build fountains in domestic and urban areas? Because we find it interesting. Little water gardens that you have in Japanese culture, or you go out west and you just see large cascading, or even like New York City. There's these cascading waterfall features that are set there in downtown. It's an appealing thing. So it's an aesthetic, it's an applicable, and it's a necessity for us. So it serves a lot of different purposes. So what are the numbers? Because it's kind of supposed to be a science topic. Sometimes forgetting about that. So how is water used? So based off of the most recent survey that I can find, roughly 80%, 79% of water in Oregon is used for irrigation. So all the food and animals that we have, most of the water, consumable fresh potable water, is used for that. Roughly 80%, 79%. 10% is used for fish hatcheries or aquaculture. So rivers in Columbia and Marion Forks and the other fish hatcheries up and down the Cascades, that through water that goes through, the water that goes into the pens, all that water is kind of factored in for aquaculture. So about 10%, pretty sizable portion in Oregon is used for fish. 8% is your municipal domestic water supply, so drinking waters. These are your reservoirs and other water towers, things that through the pipes through your houses, etc. 8% of the water in the state is used for that. Fresh water, about 2% and 1% are used for other. So hydropower, hydraulics. That's water, steam, that's stuff that drives industrial industry. That all takes place, plus, mining and livestock and some others. So, but generally speaking, the thing that owns water in our state at least is agriculture. Okay, now, that's all kind of fun and interesting, like, ooh, pretty and appealing and aesthetic and useful, but that's not the only use. When you think of water, how often do you think about it? Did you think about it this morning when you woke up? Did you think about it when you turned your faucet on, or when you got the water out of the little spigot there? I generally don't. probably think about it more than the average person because it's my job. So water as a whole is underappreciated by society. It's thought about, but it's not genuinely appreciated. So, first and easiest question I have for you is, where does the water come from? Or water come from in your lives? You know, you ever think about it? Who thought about where that water came from that filled up that jug? Okay, one person? And so it's sort of a setup here. So when we think of where water comes from, you can go for the more natural aspect, because we're tend to be environmentally conscious here in the Northwest, so we can think of the rivers and reservoirs. I've spent a lot of time in field work, working in the Western Cascades, outside of Salem, Detroit Lake, and then down to Guerin Island, which is the city of Salem drinking water supply. So I'm familiar with both the source area of reservoirs and rivers, but also, I think of water, I think of treatment. So I'm a Chicago native. I've never had a water tower, but I know there's a lot of places in small rural parts around the country that is sort of, when people think of where does the town of water come from, they point up to the water tower that's in the town. However, as we mentioned before, globally speaking, and even in the state, when you have eastern and western split, groundwater is the primary source of water, well water. You know, if you're not on a septic system or a sanitary system, you're pulling your own well water, that's coming from the ground. So there are different considerations for, you know, the old classic of going camping, which is what I always thought of, because once again, I grew up in a city, we had water at the tap, so I only use these little crank things when I went camping. But there's also, of course, more industrial uses, because whether it's irrigation or personal use, wells supply most of the water, at least in Oregon, in the eastern part of the state. So water use statistics. The United States each year uses about 150 trillion gallons of water. And this is all just summed up with that potable, consumable, fresh water that we use. Oregon, if you factor out the percentage of population in the state compared to the country, Oregonians use about 3 trillion gallons of water, which is about half the size of Crater Lake. So every 2 years we would drain Crater Lake in order to provide the irrigation and municipal supplies and everything else that we need water for. Most of the water in our state, luckily we're a water-rich state because of the Cascades and the Willamette Valley, so we have a lot of surface water, plus a lot of the population lives in those areas, so reservoirs serve surface water that serves the where water's coming from. So 70% of the surface water, or the fresh water we use, is surface water. Eastern part of the state, not so lucky. Most of the other 30% is used as groundwater. If you do the simple math of the amount of water consumed by the population of the state, the average person uses about 170 gallons of water per person per day. Now that may seem like an exorbitant amount. I've tried doing the math, and there are some online calculators and tools, and you see this number fluctuate. I've seen it from like 104 to like 240. But it's just the idea that every time you take a shower, wash the car, do the dishes, flush the toilet, every time the manufacturing water that needs to do to design and build the clothes you use, the car, everything that's part of your life, the food that you're eating, the water you use to produce that, if you divide it out, this isn't as exorbitant of a number as you might think.
So that 170 is agriculture to grow your food, too?
Yes, that is basically taking the idea. We know that there is X amount of water in the state that's being used, and this is the wide population. You just divide the two, that's what you're being assigned, basically. Now, we talked about some of the more charismatic parts of water. We're sort of neglecting one of the big water uses that we use as people, particularly Americans. So water is really, really underappreciated, and we know where we're going with this, right? Where does your water go when you flush? How often do you sit there, just finish a nice, whatever, stand up, hit the lever, and walk away, and like, that water is going, away. It's going away, and that's all that matters to me, and that's why it's important. But there's a whole bunch of professionals and people who work their entire lives to make sure that that water, that sanitary sanitation makes a difference. So water provides a valuable service that is often super duper underappreciated, and that of course I'm talking about is waste removal. So when you think of waste removal, there's sort of the basics, like we all know about sewers. We've seen or heard or smelled those before. We've gone through, wastewater treatment plants. How many people have ever taken a wastewater treatment plant tour? Oh, amazing. Do they have the water fountain that gives you the purified water that you can taste at the end if you want? I know they do that in Durham. That's the one I went to. It's just a blast of what they can do, and then all of the resources they can pull and extract out of that. Where I know, once again, Durham is one I'm most familiar with, is my work on the Tualatin, where they make fertilizer out of the waste and sell that back. They sell the water to like breweries, and there's now like a poop beer company that like makes their filtered water based out of wastewater effluent that's been purified. The big pipe on the top is a picture of the big pipe. If you guys are familiar with the big pipe project in Portland a few years ago, where they have a combined sewer overflow system of septic and runoff. So every time it rained, if people were flushing their toilets, a lot of the water would fill up the sewer, and you would have to have these release events on the Willamette River where they would basically discharge unclean water, and you'd see warnings for E. coli and fecal matter and all this other stuff. It would happen about 40 or 50 times a year, depending on how rainy of a year it was. After the big pipe project went in, they now average between 1 and 3 discharge events a year. So it's a win for keeping the amount of waste from entering the river as it once was, but it's still no longer. It's not a perfect solution by any means. So, as somebody who studies water quality, if you think of dirty water first, our minds immediately go to pollution when we think about water quality and what we can do to fix that. So let's think about it for a second. What are we finding in our wastewater? This is treated wastewater, mind you. So, how many people here have ever taken a medication? How many people drink coffee or some form of stimulant? Alcohol? Go down the list. How many people use soap when they shower? How many people do laundry with soap? So the idea here is all that material that you're adding to the water supply, even after it's being treated, is not being removed from it. Because in a lot of cases, wastewater treatment facilities, when they were originally designed, in a lot of cases we're talking 40, 50, 60, 100 years ago, they were designed to take out viruses, bacteria, and other pathogens. They were not designed and developed to take out unmetabolized, let's say epinephrine for some chemical that popped in my head, but unmetabolized caffeine, for example. So there's now this whole new stretch of, or new discipline of science and hydrology, where they look at emerging contaminants or contaminants of emerging concern. And these are things that we weren't even thinking about 30 years ago. Now, over the last 15, 20 years, we're now thinking about them. We're only starting now to monitor and figure out what effects this type of stuff will have long term. So I have colleagues who work and they'll do sediment tests and they'll find caffeine and estrogen and all those other chemicals, from birth control pills to cocaine to whatever, in the soils. They'll find it in bugs and they'll find it in the fish. Well, if it's making it that far up, I guarantee you it's hitting us in some cases. And there are some tests that I have seen done for flame retardants in particular that are endocrine disrupting, if that term means anything to you. Your lymph system that allows how your body basically functions get messed up by your exposure to certain chemicals. And these are endocrine disrupting chemicals. Flame retardants is one of the most popular, most well-tied one to that effect. And everything we wear, sit in, these tablecloths, our rugs, in our houses, all those materials tend to have flame retardants in them. So there's been studies looking at, this is where it gets traumatic, I'm going to lower everyone's mood for the day, but looking at breast milk in babies and other things that, due to exposure of crawling on the rugs, and, dust materials, fibers, all that stuff carries with it potential chemicals which may have an effect on you. Well, none of that stuff is treated in the water either, or is starting to. Some of it is actually starting to be looked at, but we don't even know what to look for, let alone how to address it in some cases. So, yes, personal care products, the soaps, the detergents, plastics, that seems to be the new thing in the last 2 or 3 years, microplastics. We're talking about those. We have our PCBs and PDHs. These are basically your oil chemical plasticizer materials that oil spills and other kind of pollutants that make it into the water supply and then and then of course there's mercury and some other pesticides that you might have on your food that you eat or wash off in the sink as well. Okay, so water is also convenient, which is a nice property of it as well, because water flows downhill, right? The king at the top, I always describe the analogy, but basically poop flows downhill, so the king of the hill is always the one who's highest. In this case, that's a property of water that we take advantage of. You know, we are actually using gravitation, or gravity to move water through our storm sewer system. It eventually makes it out to lakes, rivers, reservoirs, and beyond. That water, similar, as you might imagine, if our wastewater, that's sewer water that's being treated, does not remove chemicals. Untreated water, water that's being washed off the surfaces, has all those same things plus more in greater abundance. You know, that oil stain that came off that car parking lot, when you go back the next day after a storm and it's gone, it didn't just disappear. It got carried and moved somewhere else, and usually attached to water, because water likes things, and things like to attach to water. So all the same things that we might find in treated water, we also find in untreated water here for storm runoff. So the same thing, the plastics, the flame retardants, the petroleum products, we factor in industrial automotive type stuff, fertilizers, pesticides, herbicides, all the material that goes on the surface is not always consumed or used or metabolized by the things that it's used on, and will make it into the water supply as well. Yay. Positive, right? Okay, so water is in fact very, very complex. So now we're going to go a little bit more in depth about different aspects of water that we care about, not just the pollutants, but what's in our water, right? H2O, we know that there's 2 hydrogens, 1 oxygen, that's sort of the base, but we'll never see pure water. So there's other stuff that we tend to find. It all varies depending on what water we're looking at, right? If we're looking at tap water, it's much different than we go down to a wetland, or the water that's out here in front versus the water that's rolling down the curved sewer line out front. So what do we think of when we think of water? Well, there's the obvious. There's the things you can smell, taste, and see. So you can see polluted and smell polluted sewage water, right? That's pretty obvious. But there's also other things that you can't. So these are the things that are dissolved, or in such a fine percentage that you're not actually able to make out or taste or notice the difference. So there are also things that are alive, you know? There are things living in that pond that are not just water, but rely on the water to live. So these are not just the bacteria, but viruses and amoeba and plants and bugs and everything else that is in the water itself. And there are things that are not alive that are in the water. Dirt. As a person who studies sediment and dirt, that is where most of my energy and information goes. I care about how much material is leaving the surface and making it into the river, and how it's being carried downstream and what it's doing as it's being carried downstream. So things that are living, things that are not. There's also a mixture of things that are dissolved versus things that are particulate. So things that are particles that are floating in suspension. Dirt doesn't necessarily dissolve into the water that you can't tell, but salts do. You know, I don't know if you've ever done the experiment of giving somebody a glass of water and having salt water. It's like, which one's salt water? You can't tell by the look or smell. It's not until you taste it that you can, because salt will dissolve, and you won't be able to see it as an optical property. But there's also a variety of different salts. It's not just sodium chloride. We're dealing with sodium, potassium, calcium, etc. Then there's also the organics. There's things that are living in the water. I believe she took off the presenter before mine was talking about harmful algal blooms and cyanobacteria or blue-green algae. That's living stuff that's in the water that changes water from blue to green, and you'll see it, you'll smell it, it'll have an effect on what's going on. There's the chemicals we kind of alluded to with the treated and untreated water, that if it's on the surface, in the air, on our bodies, or around, chances are it will find its way to water, and then they'll be carried down, and you'll then be able to test and find those materials, those substances, those chemicals in the water as well. This is your idea of general pollution. And then dirt. I like to talk about dirt, so I'm going to give it another shout out to sediment. And then of course there's everything else. Like this doesn't define everything that you can possibly see, but it kind of gives you an idea. Yes?
Do you know what that picture is of?
That is the Upper Klamath Lake from probably 2014.
Is it algae?
It is algae, yes. Okay, and now to end on a little stewardship message and an environmental conclusion for everybody. Water is our responsibility. This, I hopefully, should go without saying, but just the realization and awareness of what's going on with water is important for us because we rely on water to survive, as does everybody and everything else. So, to finish up, a little quote from the Round-Aged Mariner, which entitled my talk, or gave me the motivation for the talk. Day after day after day, we stuck, nor breath nor motion, as idle as a painted ship upon a painted ocean. Water, water everywhere, and all the boards did shrink. Water, water everywhere, nor any drop to drink. Who's familiar with what this image might be?
Oil spill.
Oil spill from?
I don't know.
This was the Gulf spill, so the Event Horizon one. That was back in 2013. I'm a little rusty on the numbers now, it's been a few years, maybe 2011. Earlier in the decade. So when I saw this image, once again, it kind of inspired this entire talk that I was giving. That I used to do literature in high school, and I loved Round-Aged Mariner and water, water everywhere is sort of like the running cliche within the hydrologic community. So I decided to take that when I saw this image. I'm like, okay, that's a good thing to end on. Like, it matters how we take care of water because we rely on water. And we can always use good imagery to kind of get people to think about it. Maybe give them a nice story to wrap that together. Who knows? Maybe somebody will actually act on it and show concern and actually participate and engage, which is all we can ask for. So with that said, and with your weird picture of things you can find in water, iron, steel, handguns, so you never know what's going to be out there. So I will now have some fun with you guys and see what we learned and what we're aware of and what we've taught in our different classes. So, first off, true and false. Water contracts or gets smaller when it freezes. True or false?
False.
Nice. There's always one kid in class that doesn't know that. Okay. Second, water has a high surface tension. True or false? Can you give me an example for that you always think of? Belly flops. I always think of those little water skipper buttons that kind of run across the surface whenever you go next to a river. True or false? Condensation is water coming out of the air. Oh, yeah. When your glass is sweating, it's not leaking through the glass, it's actually sucking in water from the air. More things can be dissolved in sulfuric acid than in water. There it is, because water is a universal solvent. It dissolves more things than anything else. Rainwater is the purest form of water. False. True. What is the purest form of water? I don't know the answer to that, so there you guys tell me to leave you. Number 6, it takes more energy. So physics question for you. To heat water at room temperature to boiling than it does to change boiling water to steam. So is it more energy to heat water or to evaporate water? True, I guess it's true or false, I should say that. It's true to heat water versus to evaporate it. False. Phase changes, takes more energy. Okay, if you evaporate an 8-inch glass of water from the Great Salt Lake, you will end up with about 1 inch of salt in the glass. I gotta get more people, I only get one false. True. Oh, there's this controversy, I love this. And the winner is true. I'm trying to think of, is it the Great Salt Lake? What's the one in the Middle East, Jordan? Dead Sea verse sort of bigger than this with the amount of salt you can do. Right? I don't think you can sink in there if you try. I'm very curious to go there someday. Number 8, seawater is slightly more basic, so lower acid, pH value is higher than most fresh natural water. That is correct. And why is that? Because it's dissolved stuff in there, and salts tend to cause things to be more basic rather than acidic. 2 more. Raindrops are tear-shaped. What shape are they? It's actually closer right there. So it is false. They are the shape of Hershey Kisses. Something to know. So they have the same teardrop shape at the top because of, coming down, but due to surface tension and atmospheric pressure, they will flatten, or sometimes they will actually concave inward, so you have a little dimple on the bottom of your Hershey's Kiss. And lastly, water boils quicker at Denver, Colorado than at the beach.
Define quicker. Lower temperature?
Faster. The same
At a
temperature.
lower temperature? Like, what do you mean by quicker?
If you set your stove to 212 degrees, any oil, how long it takes.
True.
That is true. And that basically, once again, has to do with atmospheric pressure. The more air above you pushing down, the harder it is to cause that phase change of heating water. When you're at higher elevations, you have less atmosphere, so there's less tension pushing down in the water, so it does cook and evaporate faster. So that's all I have, and I think it'll keep you guys on relatively good time. It is 11:34. Thank you, and any questions? Take it away.
So I was looking at your picture of the really dirty water, the water with a lot of soil in it coming down from one tributary, and a clean one on the other. And I'm going to guess there's probably logging at the top of the...
Not necessarily. It's just a different environment. So you'll see different colors and different streams doing different things like that. There's a beautiful variety of examples. I've seen the red ones, which are usually bad. There's mine tailings and other kind of runoff, or ferric acid or some form of iron oxide that causes it to turn red. In this particular case, this may be, there could be a landslide. There could be forestry, extra runoff. It could be one of them is coming from a farmland that's recently tilled versus one that's not. So it's a variety of reasons, but yeah, there's generally going to be some more soil exposure, of course, in that particular watershed or that drainage than the one adjacent to it.
You said you're a landslide expert also?
I pretend to be one, yes, actually.
What kind of projects and studies are you doing with landslides right now?
Right now, most of my stuff is focused on post-wildfire, so I go out and do assessments for flooding and reflow risks or landslide risks after wildfire. So that's my short answer. So,
Have you been in the gorge?
I was on the Oregon Area Emergency Response team that went out after the Oregon fire. So I have a whole talk on that too. But I'm also looking at computer learning for threshold rainfall intensities in the Pacific Northwest, if that matters. That is a journal review.
The area on snow events?
I've looked a little bit at rain snow events, atmospheric rivers, the El Nino, La Nina, decadal oscillation, all the different kind of things.
Yes. Later question, is water wet?
Oh God, this happened to me. So I don't know the answer to this. I know it's a trick question because, like, no, water makes things wet is the punchline. I don't know. I know oil is not wet. I can tell you that.
I just asked because students ask me.
Yes, they always ask that question. So I know oil is not a liquid, so it can't make you wet like water. But water, whether itself is wet or it makes things wet, that is a grammar thing that I'm not going to fight with. I like the Oxford comma, I'll tell you that much. So AD style is always been the main to me.
Water is wet.
See?
I agree.
Water is wet, cohesion. Electron bonds. Hydrogen bonds. Okay. I think we're good. Unless somebody else has something pressing. Okay.
I just want to come back to the pollutants, like what's being done and at what level, what's being done about the pollutants. So we have sewage and runoff. Who's responsible and what's being done as far as use?
Everyone's responsible. You can take ownership for your own actions. Oh,
Totally, I totally agree. So we vote by what we buy, we vote by what we put in, but systematically, our system's not set up for success right now. So what's being done? Is there anything being done?
There's always something being done. It's being done at different levels by different organizations, and it goes through different phases. Is the short answer. Like I remember, like this dates back, but I've now served under 3 different administrations, and I remember when I first started, arsenic had a certain threshold, and we're unable to meet it, so it's raised the threshold, and now we're meeting it all the time. That's probably not the answer you want to hear, but that's one way that things can be handled. different environmental regulations do change. Some of them are handled at local or state levels. You know, California has very aggressive environmental threshold standards that they have for different things. The city of Portland is going to have higher threshold standards than other places. Certain drinking water places are being retrofitted to address issues as they become aware or have resources to address them. There are researchers and investigators from academic institutions through federal and state and city groups that are actively monitoring and responding to things. So, I mean, it is something of concern for everybody, but it is being managed, from what I can tell, as best as possible for the moment. And it can always be improved, but a lot of that just takes time, awareness, and income.
Takes funding from the legislature to fund the rent.
Yeah. And that fluctuates depending on who's in charge and what the priorities are. Yep.
So I have a question. I have a question about pharmaceuticals, and this is it's just a curiosity for me.
Yeah.
They're saying that there's so many pharmaceuticals in the water, and fish are affected by antidepressants and stuff like that. And so I heard a story on NPR last night about pharmaceuticals that are washed off the equipment in pharmaceutical companies in their actual buildings, and they enter the water system. So I just can't believe that everyone flushing their pharmaceuticals down the toilet, because I've never done that, makes the water have pharmaceuticals in it. So is that just us peeing out the pharmaceuticals?
That is the short answer. So, yeah, the disposal of pharmaceuticals and medications, yeah, a lot of people will just generally just throw it away versus flush. Some people of older generations have learned that's the way you dispose of it, is to actually flush. But kind of tangential to your question, one thing that I remember learning years ago that blew my mind a little bit was like Roundup, atrazine, some other chemicals tied into that. What source area do you think is the primary source of weed killer and Roundup? Lawns. It's domestic. It's urban. So, you know, people like to blame agricultural lands for being these sources of pollutants and runoff from fertilizers and from pesticides. It's actually domestic use in urban areas that is a larger percentage of, in this case, Roundup, source area than it is in agriculture. So when it comes to pharmaceuticals, same thing. You can blame a point source from a factory that manufactures it, but when you have 7.5 billion people on the planet and everybody takes a Tylenol when they get a headache, you're not going to metabolize all that acetaminophen. Somebody's going to make it out. How much and where it goes, that varies, of course. But yeah, it's most of us.
Yeah, send off of the get pirates here. We're gonna look at it and give it straight. We're gonna see a little bit more sediment loss coming down all the creeks today. Just way to check out the creeks coming down. Is there a net loss of sediment? Are we balancing out? Do we have net loss or gain of soils in Oregon?
I don't know an answer to that. Like I have not seen any significant issue. I know that coastal, I've done work in Tillamook, and I know in Meatharts Bay there's sedimentation filling in along coastal streams, and navigation issues and having to dredge and that sort of stuff. But when it comes to the Cascades and the Willamette Valley, I don't know anything about sediment loss being an issue. Okay. Well, thank you very much.